Hello friends. So in this week we will look at the indoor air pollution monitoring methods, mostly focusing on the physico-chemical monitoring. In this lecture we will have some introduction and some sampling methods. So the physico-chemical pollutants are, one can say, the inorganic gases such as nitrogen oxides, carbon dioxide and carbon monoxide, ozone and several others that we have already looked in the earlier lectures. And we can also say they include particulate matter such as PM10, PM2.5 and PM1. The measurement systems for these parameters can be characterized based on several aspects. One would be based on the sampler mobility. So it could be a personal sampler, a portable sampler or a stationary sampler. And there can be different operation mode. For example, active sampling or passive sampling or continuous or online, basically meaning real-time sampling, or discontinuous or offline sampling, in which pollutants will be collected on filter or some other means and then be analyzed in the lab. The output characteristics would be like, for analyzers there would be instantaneous, otherwise we will have collectors and then they will be analyzed in the lab. So based on mobility, this is how a typical this is how a typical sampling kit which is mobile may look like, which basically contains a lot of things. We have some pumps, we have some sampling material, then things like tapes may be there, some flow measurement device or calibration stuff could be there, and several other probes or samplers will be there, and then other things such as stationery and markers and stuff. So the idea is that one would be able to take some handheld sampling device and take it to the field, take the sample, then seal the sample and bring it for analysis, or take the sample in a form or adsorb the sample somewhere and then take that media where the sample has been absorbed or adsorbed to the lab and then do further extraction or analysis. So these are sort of mobile samplers. The other thing is a personal sampler. Now, since often we are interested in the exposure of a person, the person is actually not staying in one place. The person may be at home, the person may go to some other place, it may go to a like workspace or a school or even an outdoor space. So the exposure of the person to any contaminant is changing depending on where the person is. Is the person at home or petrol pump or school or office or a market? Each place will have a different particulate matter or ozone or any chemical signature, and the exposure will keep on changing. So if you want to get a true exposure, we cannot put a sampler here, put another sampler here or another sampler here. A better way would be to put the sampler on the person itself. So wherever the person will go, the person will take the sampler with them. So in this case, this person, this is basically a pump and this is the sampler which is sucking the air from the breathing zone of the person. So it is, in a way, the person is breathing the air in this zone and a probe is basically sucking air from this zone. And in the probe one can have filter to take particulate matter, or one can have some sorbent to absorb some gases, and this is the air being pulled through by a pump. So if you are collecting particulate matter, there can be a filter holder and filter here, and this place is open to the air, and the air is sucking through the pump. So the PM will get filtered on the filter paper in this filter holder, and this PM would be the PM that a person is inhaling every time. So these are highly specialized, or in a way these are a very nice way, I think, to get the exposure of the person to the contaminants, regardless of where the person is going. So we will have a good profile of how much this particular person is exposed to, for example, every day. So we have seen the mobile samplers, we have seen the personal samplers. Next would be simple stationary samplers. So this could be a stage or multi-port sampler, where one can have filter papers or any kind of storage or sampling media, and air is sucked, and the sampler is stationary, meaning we will get the air quality in this region where the sampler is situated. So spatially we will be always at the same place. Of course, in terms of time, we can have the sampler here for 1 month, 1 year or 10 years. So we will know how the quality of the air has changed over a long period of time, as long as the sampler is there and being functioning. Then we have the offline sampling methods, which can be passive sampling method, which will rely on the diffusion of the analyte towards a collection material, where basically we will have the sample collection happening. In active sampling, we would require a power source such as a pump or a vacuum to create a force to suck the air through the collector or the analyzer. Collector if we are collecting the sample and taking it, or the analyzer if the air is directly being analyzed, or a sensor. First we will look at passive sampling. In passive sampling, the mode of collection is through molecular diffusion. The process is that a gas from outside the passive sampler will diffuse through the sampler body and get attached to an adsorbent. And these materials or adsorbents would be generally impregnated with some reagents that can interact with the target contaminants, and then they will form a quantifiable product. In that, the contaminants will get attached to this adsorbent, and then later we can dissolve these contaminants from these adsorbent and have them analyzed in the lab. These passive samplers have different geometries, and they can be of radial type, filter type and tube type. The basic principle behind the operation of passive samplers is the diffusive mass transport process, which is described by the Fick's law of diffusion. These samplers will capture the contaminants based on diffusion of the analyte towards the material which will sorb the analyte, and the interaction between the suitable reagent on the sorbent and the analyte. In general, it is considered that the sampling of such samplers or sampling from such samplers will be economical and noiseless without the requirement for power supply, and the samplers themselves are easy to install. because all we have is a box or a tube, and this can be, one can go anywhere and install the sampler and come back and then go after the period of sampling, which could be 1 week or 1 month, and collect the sampler and then extract the analyte and analyze it to get an average concentration over that period of time. The sampling approach thus can be used also to simultaneously determine mean concentration of single compound or multiple compounds in several places over long periods. So as I said, one can just put the sampler at any place and come back after some time. Now, as we know, or as we have seen just, and we will see again, that each compound of interest maybe have affinity towards particular sorbent or particular chemical with which the sorbent is treated. So in principle, if we want 5 gases to be analyzed, we can make 5 such samplers with different adsorbent properties and put them together at one place, and then come back after 1 week or 1 month or whatever duration of time and collect all those 5 and do the respective extraction process and conduct the respective analysis for quantification. That's why this sampling approach can be used to simultaneously determine mean concentration of single or many compounds in several places over long periods. So we go one place, we install, we go another place, we install, and then we can collect after several months or 1 month. So we have a very good spatial coverage and temporally averaged information. First we will look at the radial flow type of samplers. So these radial flow samplers can be commonly used for a variety of gases: NO2, CO2, HF, HCl, NH3, SO2 and ozone. The radial geometry of such samplers allows for a higher diffusion rate into the sample and towards the adsorbent, and because of this we will have a high sensitivity for determining the concentrations of these compounds. Because the diffusion rate is high, more and more compound may go and get adsorbed to the surface, thereby increasing the concentration and the mass of the analyte on the adsorbent. So when this analyte is extracted later, the amount will be quite good for doing analysis with any of the instruments. In general, and we will see the sketch, the adsorbing material is contained in a coaxial cylindrical cartridge, and the extracted analyte can then be analyzed by ion chromatography or spectrometry or any other method, whichever is suitable for the analyte. So this is an example of how one such radial sampler may look like. So this is the sort of holding stand or holding hanger for the sampler, and the sampler is the cylinder itself. So here you see it is sort of attached to a wall, and this is our sampler which is extended through the holder, and this is the schematics of how it may look like. So this is our passive sampler, and this dot dot dot, this is the adsorbing surface. So this cylinder surface is the actual adsorbing surface, and we have a diffusive surface above it, which is here. So the analyte will diffuse through this diffusive surface and reach the adsorbing surface and become adsorbed to the sampler. This is another view. So these are quite small in size, and here is our sort of the adsorbing surface, which is inside the inner tube, and this is our diffusive surface which is the outer tube, and then this is the typical airflow or the airflow which has been reported in one of the samplers of around 80 ml per minute. So one of these samplers, which is the radial sampler, the outer cylindrical surface will act as a diffusive membrane. So the gas analyte is being diffused. The gas molecules will move axially towards the adsorbing surface. The adsorbing cartridge, the steel mesh looking kind of surface, is impregnated with the appropriate chemical that is needed to adsorb the chemical to be analyzed. So this coating could be of this appropriate chemical, which is triethanolamine for NO2 sampling. It could be silica gel coated with 4,4' dipyridyl ethylene for ozone, and activated carbon or graphite carbon for the VOC analysis. The other type of sampler is this Palm's diffusion tube. The idea is that the tube will be open at one end. 2 to 3 stainless steel mesh discs coated with adsorbent. So triethanolamine TEA for NO2 for the other end. So this is how the tube will look like, and see, it is only about 7 centimeter in height. So we will have the open end. This is our open end. The screw about 1.5 centimeter wide. There is a screw cap which will basically seal the diffusion tube so that the contaminants before sampling nothing goes in, and after sampling we can again close so nothing goes in after sampling. And this is the open end. 2 to 3 stainless steel mesh discs coated with adsorbent, which is TEA for NO2 at the other end. These will be our 2 to 3 stainless steel meshes here, and the end is capped on this side. And these stainless steel grids coated with TEA will be the adsorbent for NO2. The samplers are then mounted vertically with the disc at the top end. So this is the orientation how we will install these samplers, with the disc at the top and the opening at the bottom. The molecules will then diffuse through the opening. So somewhere like in this direction into the tube, and then they will go and adsorb to the adsorbent, which is our TEA for NO2. And this is the idea about how to have a diffusion tube working. Tube type samplers are commonly used for NO2, CO2, SO2 and O3. The collection is these gases are collected based on diffusion of the molecules into the tube containing the adsorbent, and such gases can be analyzed by ion chromatography or spectrophotometry. The next type of passive samplers would be the filter type passive samplers. These samplers are commonly used for ozone and NO2. Now filters are used to collect, and these filters are basically impregnated with material with a suitable solution such as nitrate ion or triethanolamine to react with the contaminant. And then when the contaminant is sort of adsorbed to this place or reacted to this suitable solution or suitable chemical, one can later extract and analyze them. The one type of passive samplers we will look at closely is the Ogawa sampler, which have been used for analyzing ozone, SO2, NO2, NO and NH3. So the way they are made is, first there are several components: a diffusive cap, a stainless steel screen sometimes, then a collection filter pad, a filter ring, a backing tab, and the body where all these things are fitted. Again, we will look here. So we will have the diffusion cap, which is your diffusion barrier. Then there is a screen, which is stainless steel. Then we have the coated filter. So depending on the gas one wants to sample, the coatings will be different. Then we will have the support screen. And we will have a solid Teflon body into which these will fit in. This is how these may look like. So diffusive barrier, then diffusion, this stainless steel screen, then the filter, coated filter, then again we have the stainless steel screen, then we have a filter ring, this one, then we have the backing tab, and then we have the body. The filters will have different adsorption reagent based on the gas that have to be analyzed. So for NO2 we will have triethanolamine TEA as the adsorption reagent. This is adsorption reagent, not absorption reagent. For NOx, the adsorption reagent would be TEA plus PTIO, which is 2-phenyl 4,4,5,5 tetramethyl limidazoline 1-oxyl 3-oxide. For SO2, we can also have triethanolamine TEA. For ammonia, we will have citric acid, and for ozone, we will have nitrite ion. And once this adsorption is carried out, the later analysis, as said earlier, can be done by ion chromatography. So once we have done this sampling, how do we actually calculate the concentration of the gas in air, which was actually our primary objective? So if we use the Fick's law of diffusion, the flux J, which is the mass of the analyte per area per unit time. So flux of gas from ambient air to the reactive surface of the sampler is derived using the Fick's law of diffusion, which is J equals dB multiplied by delta C, which is the concentration gradient, and delta X, which is our diffusional distance. So dB is the bulk gas diffusion coefficient, delta X is the diffusional distance through the sampler, and delta C is the concentration difference between the air concentration or the concentration of gas in air and the concentration at the reactive surface, which will be Cs. Now, if our adsorbent is very effective, we will have a rapid and complete gas trapping. And due to this rapid and complete gas trapping, we can consider Cs to be 0. So once we do this, we can simplify and get mass of the gas accumulated over a time t. This will be flux, which was mass per unit area per unit time. When we multiply it with the cross-sectional area and the time period of sampling, we will get the total mass of the analyte or the gas accumulated on the adsorbent. So M equal to J times A times T, and we know from before J is dB multiplied by delta C divided by delta X. So we will get the expression M equal to dB A T delta C by delta X. If we rewrite it, we have dB by delta X A T multiplied by Ca, because Cs was 0. Now dB is known or can be known through equations derived using separate experiments. A and delta x are dependent on the geometry of the sampler and can be known, and T is our sampling time, which we know already, and M we will determine from the lab work. So all these things will be known and Ca could be calculated. So if we rewrite this, we will have Ca is equal to M by T. Basically this T will be brought here. So we will have M by T equal to MB multiplied by Ca, and MB would be dB dBA by delta x. This will be our MB. This MB can be termed as a mass transfer coefficient or the sampling rate. So A is known, delta x is known, and dB can be known from literature, so MB would be known. In lot of literature, you could also find this written as follows: C equal to M by UT. And basically the idea is the same and the principle is the same, that after the sampling time, so once the sampling is over, the chemical will be dissolved from the adsorbent, and the mass of analyte, which would be NO2, ozone or anything else, that would be determined. So if M in milligram is the mass of the analyte collected after sampling time T in hours, and U is the uptake rate, which is reported by the manufacturer in meter cube per hour. So this will be our sampling rate or the mass transfer coefficient, which we just derived here. Then the concentration will be given by C equal to M by UT, which is exactly the same as this. If we rewrite this, we will have Ca equal to M by MB times T, capital M, this is capital M. So this MB is basically our U here. So U would be depending on the diffusion coefficient, so dB of the target pollutant. So we can derive the concentration in the air using this passive sampling method. And as we have seen before, it depends on the diffusion coefficient, is directly associated with the cross-sectional area and inversely proportional to the length of diffusion. So we go back, this is directly proportional to diffusion coefficient, surface area also, and inversely proportional to delta x, which is the length of diffusion. So we have derived this equation and the method to obtain concentration using the passive samplers. For Ogawa type samplers, the uptake is given as alpha x with all the conversions between ppb, ppm given. So they often report Cx is equal to Ax multiplied by M divided by T, where X is any gas NO2, SO2, NH3 or O3. The Cx is the concentration of gas in ppb. The M value is the quantity of X collected in the collection element in nanograms. T is the sampling time, and alpha x would be the converted uptake rate into concentration, so ppb minute per nanogram. So that will give our concentration Cx in ppb. There are different alpha values for different gases. For NO2, the value is as this and is inversely proportional to the relative humidity, the ambient temperature and the saturation water vapor pressure also. So P is given as 2 Pn by Pt plus Pn, which is Pn is the saturation vapor pressure and Pt is the saturation vapor pressure at temperature T. So this is inversely proportional to this P value, which is as this. So the response will be different and also will be in relation with the relative humidity. So the proportionality with the saturation water vapor pressure will have to be seen when it is calculated at time T, at temperature T. SO2, alpha SO2 is given as a function of inverse of temperature with a certain coefficient 39.4 and T here is in Celsius. Alpha NH3, the coefficient is different, but the exponent and this part, exponent part, is the same. For ozone, the alpha is also inversely proportional to the sampling time and is calculated accordingly. The factors that will affect the concentration determined by passive samplers would be the temperature, pressure, humidity and the air velocity, the concentration of the analyte, response time, sorbent type or reagent saturation. They will influence. Also influencing the results would be back diffusion, loss and the decomposition of analytes. The next is active sampling. This active sampling approach requires some mechanical equipment, for example pump, to suck the air and pass it through the sampler. So here I will show this one. We have the pump and the sampling media, and this pump is sucking the air through the sampling media. Sampling procedure like sorbent media preparation and other apparatus for collection are same, and other means are also same, but instead of relying on passive diffusion, we are doing a active sampling. So we have the filter or in sorbent here, and we will have in this case particle filter, and we can have different sorbents here. So sorbent will be sucked through. We can have different means of air flows. So we will have a filter here. Here we have an impaction surface right here. Here we have a denuder coated with the solvent, followed by a particle filter, followed by a PUF or 10x sorbent. So the idea is still the same. We are trying to pass the air through a absorption surface or a filter surface. Only instead of relying on diffusion, we are forcing the air through and collecting possibly more amount in a shorter time. So active sampling is economical, but it will need power supply. The sampling time would be more short term and typically sampling for a few hours. Then the collected samples can be processed for solvent extraction before analysis on instrument, or directly analyzed with gas chromatography or spectrometry using commercial samplers and commercial analyzers. So in summary, we have seen now various type of sampling methods, and they are to be chosen by the requirements of the study. We can have mobile sampling, personal sampling or stationary sampling, and the sampling method could be passive or active.